Oh, good morning. We're still hanging out and chilling out in section 3.1. And what we're looking for is, let's see, there we go. What we're actually doing is we're looking for relationships between f and f prime, okay? And we have found an algebraic derivative. And had you had it in pre-calc last year already, which is right here written in purple I got, and that's our algebraic derivative. And had you done enough of these, you would have already found the connection algebraically between a polynomial and its derivative, but that's okay, we're going to get that soon enough. And what we're also looking here is we want to look at a graphic relationship. Is there a graphical connection between f and f prime? And what I'm asking there basically is, do the slopes, okay, the derivatives at different x values on f of x also follow a pattern, and can those values also make a function? And the answer to that question is yes. And so like I said, what we're going to do is we're going to explore a graphical connection between an original function, what the graph of the original function looks like, and what the graph of its derivative looks like, okay? And it's actually it's kind of cool. So what we're going to do is we're going to consider a function, f of x equals x cubed minus 4x, one of them. We did this algebraically by the derivative, and we found the algebraic derivative was f prime of x equals 3x squared minus 4. That other parenthesis doesn't need to be on there. So what I need you to do is I need you to grab your CAS calculator, and I would like you to enter this function in here, okay, f of x equals x cubed minus 4x, and I want you to place the windows so you're looking just at -3 to 3 for the x's and -10 to 10 for the y's, okay? So why don't you do that quick second. And hopefully you have your calculator, and I'm just going to pop mine up here quick for you and remind you to change your windows. You just go Menu, Window Zoom, Window Settings is the easiest way. -3 to 3, I like to make my x scale in this case at 1, and my y went from -10 to 10, and again that scale is at 1, and you hit OK and you get this pretty little graph that we're looking at here. And what we're going to do with this graph is, my question is, okay, can we find a graphical connection between the graph of f and the graph of f prime? Is there a graphical connection between these two? And I really want to talk about something here. And what we're going to be doing, okay, we are going to be sketching a graph of f prime. And the way we're going to graph that is we're going to find a bunch of ordered pairs that would make up our f prime graph by finding slope values on f of x. And I'm going to show you how to do that in your calculator. And it really is a big deal here that as we go through this first one, that you understand that the y value on f prime is the slope on the original function at that x value. So we are going to be making a graph that's going to be taking up an infinite number of slopes, basically, and we're going to be connecting those two, all right? So how I want to deal with this is we're going to come to the first one here. And notice my xy chart. I have x for that, and then this is f prime of x. So this is the slope, okay? It's the slope. The y value is the slope on f of x at these 5 different x values that I'm going to find. And that's what the y value on f prime represents, okay? So this is the graph of f that you're looking at there, that red graph. And what we're going to do is we're going to pull up our calculator here. And you probably don't know how to do this yet, but that's okay. So we're going to pull up our graph. And what we're going to do is we're going to go Menu, Analyze, Menu 66. See how this dy dx, that's a derivative. And we want the derivative
the first derivative we want is going to be at position 0 there. I'm not going to drag my finger around. I'm just going to hit a 0, and I'm going to hit enter. And I can see that at x equals 0, what that means is the slope of the tangent line right here at x equals 0, the slope is -4. So what I'm going to do is I'm going to come back here and I'm going to say, 0, -4, and I'm going to make that point on my graph. Okay, so the slope here is 0, 1, 2, 3, 4. My whiteboard is really acting up on me again, so I'm hoping I can make these dots. So that is the slope at that point. Now I want to go back and I want to find a few more. So I'm going to pull my calculator back up, and every time I do this, I'm going to have to give it the old menu, analyze dy dx, which is menu 66 if you do that. In the next position I'm going to find it is at 0.5 or excuse me, or a half. Oh man, or a half. And if that ever happens to you, you hit Control Escape and it takes you back where you were. And I'm going to say menu 66. My position is going to be 0.5. And I'm going to, what the crap is going on here? Go back. Menu, analyze, dy dx, and I want my position at I got to probably go 0.5. That's my problem. I got to do 0.5. Okay, so it won't give you the 0.5. I had to do 0.5. I find out the slope here at 0.5. The slope of my tangent is -3.25. So I'm going to come back here, and I'm going to fill that in here, and I'm going to say -3.25, and I'm going to say a half, so that's going to be somewhere in here, and again, Mr. Whiteboard's being a pain. I'm going to come back to my calculator, I'm going to find it, menu 66, I'm going to go at position 1, and at 1, my slope of the tangent line is -1. So all I'm doing is finding a bunch of different slopes on my curve, and I'm plugging those in here. So then I'm going to go make that point at 1, -1. So that's right about here-ish. And if we actually looked at our derivative that we found before here, okay, because we did see the derivative here is quadratic. So we know this graph that we're making, this is the algebraic derivative. So the graph that we should be making should be a parabola, okay? And I'm going to get these other 2 points here. I'm going to get -1 and -1/2 off my calculator. And I'm going to give it a menu 66. And I'm going to say position -1. So I can say, look, check it out, -1, and I'm going to give it another menu 66, and -0.5, and check it out, that's a -3.25. Okay, so what does that mean? That means kind of interesting stuff there. So I'm going to clean this down a second, and what I'm going to do is grab my pen again, and -1 was -1, -1/2 was -3.25. I'm going to plot those 2 points quick and use the word quick lightly because this smartboard is really ticking me off. Half is going to be right around here, and we can see on here, okay, I can see a parabolic shape there. Now, before we go on, because we're simply picking slopes of the curve. So like right here, when x is 1/2, the tangent line right here, the tangent line is 1/2. So that's why I plotted 0, not 1/2, -3.25, sorry. So I'm finding a bunch of slopes. What I'm doing is I'm making a graph of all the slopes on this. And quick question for you. Right here at this minimum, it looks like there's a minimum right here. If I envision a tangent line there, what is the slope of the tangent line there at that minimum? Wouldn't that be 0? So wouldn't this little rascal come right up to here
and track right there. And because over here I have a maximum as well, it's kind of a flattening in my curve really, and I can track that guy back down, and I have that one right there. So when I track those two on there, what I can do is I'm kind of just looking at some of my graph, and I'm not doing all of my graph yet, because I want to ask you a couple questions here now. So as I'm looking at this graph, all right, what I did is I have part of it. And the first question is, why would all of these values, why are all these values that I've picked thus far, why are all of those values negative? Why are the slopes between here and here, why are all of these slopes negative? And let's think about that for a second. Well, what is my function doing between my maximum and my minimum? My function is doing what? My function is decreasing. Whenever I'm drawing tangent lines of decreasing things here, check that out, what's going on is the slope of all of those tangent lines are negative, and that's why that's why that portion of the graph is negative. Okay, where is it most negative? It's most negative right here, right there. Okay, that's my most negative slope value. Why is that? Well, that's right here when x is 0. Why is that there? Well, look at that point once. We've talked about this point right there. That little rascal is a point of inflection. Okay, that's where I change concavity. So if I'm envisioning tangent lines coming down this curve, right there at that point of inflection is where my tangent lines are the most negative, and then from there they keep getting flatter and flatter, and they come back to 0, and they get less negative. That's why that is my most negative point. The other thing I want to point out to you here is, let me get rid of all those little guys for my explanation again, and I'll leave point of inflection on there. To the left here, what is my function doing over here? Okay, what's that guy doing over there? Again, envision tangent lines, tangent lines, tangent lines, tangent lines, tangent lines. Well, what my function's increasing over there, and the slope of all of these tangent lines that I just drew those lines on, they're all positive, which means the value of my derivative is going to be positive because there's an arrow on that red going down. Well, from this minimum, check it out, my tangent lines, they're small, they're very small, close to 0. Hey, check out where I am. And then the further away from there that I get, my tangent lines get steeper and steeper, envisioning something like that. So what I can do is go back forward. What I can do is I can envision all those tangent lines on there, and their slopes are always going to be positive. So what I want to do is, let that on there yet, okay? So what I'd like to do here is I'd like to try to answer this question. What is the value of the slope of f, which is the value of f prime, okay? That's these values here. What is the value of f, the slope, what is the value of the slope of f, which is the value of f prime? That's all these guys that we pulled out there. What's it doing from left to right on its domain? Well, check it out. Tangent line, tangent line, tangent line, tangent line. And if this kept going down, what's happening to the steepness of my tangent lines? Well, they're getting steeper, isn't it? So what I can do is I can see my value, my slopes are very, very steep and positive, reading from left to right. They're very, very steep and positive, and they come up, and then they stop. Okay? They're super steep, and then they're getting less positive, and then what do they hit right there? The slope of that spot. The slope of that is 0. And then from that 0, what's happening to all these tangent lines? Whoa, my slope is going negative on that red curve now, and it's getting more negative and more negative until right there, where it's the most negative,
And then where it's the most negative, well, now all these tangent lines that are coming down to this minimum here, okay, they're getting less negative and less negative until they hit what? They hit 0. So I can kind of see all that in there. And then from that minimum, all these tangent lines, well, they turn positive. I can see they turn my positive slopes, and then they turn positive, and then they get super positive and super steep. So what that's actually doing, okay, is left to right, my slopes are very steep, then they get less steep until they hit 0, and then right after that 0, my slopes start to turn negative. Then it gets its most negative at that point. Then they start getting less negative, hit 0 again. Then they turn positive, and then they get very positive, okay? So I can see that same thing on the graph of my derivative. Because realistically, this is what the y value on f prime is doing. Check it out. I'm very, very positive. And as I come down, I'm getting less positive, aren't I? Until right here. Then my slope is 0. Then my slope gets negative, and it stays getting more negative until it gets to its most negative right here, which correlates to my point of inflection. Then what's happening then is what? Well, then they're getting less negative and less negative because my graph is coming. My y values are getting less negative. They're getting closer to 0 until they hit 0. Then they turn positive, and then they get super positive again. Okay? So that's exactly what I can do. I can read that off of my regular f of x function or my f function. See, this is the connection that we're making. So what I would like you to do is I would like you to change the graph in your calculator, and I would like you to fill out the points in which I have on there. I want you to go in and evaluate all those points quick in your calculator. And I really would like you to do it because you need to know how to do this in your calculator. And I'm going to pause and let you do that. Okay, so hopefully you got all these. And remember, the y value on f prime, all of these values that we just found, they are the slope of that red graph right there at these particular x values. So when I look here, when x is -1, okay, -11 is not talking about how high, come on, you stupid thing. It's not talking about how high it is or anything. What it's talking about is the slope of the tangent line that goes through that point, okay? So we're plotting all these different slopes in this thing. So I'm going to try to make this happen. I'm going to hit, no, I'm not going to pause. I'm going to -1, -11, somewhere down here. And then we're going to go -0.5, about 1, 2, 3.5. So somewhere right in here. Come on, baby. And I'm going to leave that one. I go 0, 1. So that's right about here. Come on, baby. There it goes. And then I got 0.5. And then I got 2.5. So that's going to be somewhere right about here. And I'm just getting some random road points in there. Not -2.5, +2.5, Kruger. So, 0.5, 2 points. So I'm right somewhere up here-ish. And then I'm going to go 1, 1. About there. And then I'm going to go 1.5 down 3.5-ish. Yes, these were all picked out especially for you to be symmetrical points, okay? And then I'm 2, 11, so that little bugger's down here kind of. And there's always a couple of them. There's always a couple points that are super easy to pick off of the graph of f, because what do I see right here? And I can see that that's a flattening in my curve, and that flattening of the curve, the slope of that is 0, so that guy goes right about there. And I have a flattening in the curve right here, so that also is 0, so that guy goes right about there in that flattening. Okay, so what can I do off of those flattenings? Well, I'm pretty sure that you would be able to pretty much make a semi-decent sketch of that parabola. And what do we notice again? Okay, right about in here, you got to try to feel it. It's not easy to feel all the time, but I have a changing concave up, concave down, called a point of inflection. So because I'm changing from concave up to concave down,
I can see what's happening are the steepness of my tangent lines are going to be most steep right there, and then they start getting less steep. Okay, so it's just an interpretation of the graph. So what that's going to do is that is like a highest point for that one. Okay, so when my function, when f has a minimum or a maximum, these are good notes to write down. When the function has a minimum or a maximum, what happens is f prime, those are x-intercepts for f prime because the slope is 0, all right? And then furthermore, when my f of x is increasing, so I'm increasing here between my minimum up to my maximum. Check that out. I'm increasing. What happens is all those tangent lines, all those slope values when my function increases create positive tangent lines, and that's why between these two in this particular example, that's why all of those values are above the y-axis, because these are positive y values would reflect positive slopes, okay? Conversely, when I look here, from this minimum coming into this minimum to here, what's my function doing there that I just drew in purple? It's decreasing. And when I'm decreasing, okay, the slopes of my tangent lines are negative in value. Hence, this is why I'm all negative there. And then from that maximum, check it out, I'm decreasing again. So what I picture is all these tangent lines that I could draw, what is the slope of all of them? They're all negative. That's why from there, all these values are negative on the graph of that derivative, okay? The slope is negative, and because it's negative, I'm below, because these are all negative y values, and that would reflect a negative slope on the original function, okay? And what I'm going to do is I'm going to go to the next page, have you pause and do this whole entire problem once, see if you can make your graph on your own following the same thing that I just did. Okay, so if you went through and you found all these values, again, these are the slope at x equals -2 on f of x. The slope is -8, so my blue graph is the graph of all the slopes. But what I did is I found all these ordered pairs, hopefully you did too, and I plotted all 4 of them on there, boom, 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 and boom, and I connected them as best I could, and oddly enough, boom, it was a line, and I connected that line. Now, then I went in after, and I found my minimum value here, because that's where I have a horizontal tangent of 0, so I tracked that value up to 0, and just to explain things, well, any flattening of a curve, okay, the slope at any flattening on a curve, guess what it is? The slope is 0, and that's why that tracks right back to an x-intercept. To the left of this flattening, okay, check out what is the red graph doing here? The red graph all the way until I hit that flattening. What's it doing? It is decreasing. And because it's decreasing, that means all of its slopes are negative, and that's why all of these from that flattening this direction, that's why they're all negative y values. And then from there, from my flattening, I'm increasing again, and I never quit increasing. All of my tangent lines that I envision on there, what are they? They are all positive, which is why from here, every y value is positive to show that it's there. Okay, so what I'm going to do is, because this one's not on there, I'm skipping this note sheet. You're going to flip probably to the back of your note sheet. We're going to figure out a couple really important things, or we're going to fill out some really important things here. So if your function f is increasing, if f, the original function, is ever increasing, that means on the graph of f prime, that f prime is going to be positive. And remember, all positive means is it's above the x-axis because all those y values are positive. If my original function, if f is decreasing, Ooh, what does that imply? That implies f of x is negative. Because if it's decreasing, I have negative tangents at it. And if if f is decreasing, f prime is negative, ooh, all my points are below the x-axis. Then I come along. If f has a flattening, a maximum or a minimum, it doesn't always have to be a maximum or minimum for a flattening. I just want to identify that. What happens is my tangents at the flattenings, my tangents are 0, which means that's an x-intercept. That value is on the x-axis. And if you've put this together yet, on f, if f has a point of inflection, okay, that implies on the graph of f prime, what is it? Okay, well, not there. This didn't have a point of inflection. This graph is concave up all the time. This graph, ooh, this one had a point of inflection, didn't it? My point of inflection was right here. What did that amount to on my graph of my derivative? Let me come back to the middle one. This one had a point of inflection. What did that special point of inflection amount to on that graph? And if you didn't see it, I'm telling it to you, but I'm sure you saw it there, then f prime has a max or a min, okay? It's one or the other if you have a point of inflection typically on there. And what we're going to do is we are going to roll the dice here, and I'm going to give you a chance to sketch this graph, and then we don't know anything about the function. So all we're going to do is we are going to make a possible sketch of f prime with that. And hopefully you paused so you could get this copied down, but I'm going to come here on the side, and I'm going to see I have a flattening. I am flat at, I can see I'm flat here at x equals -2. I can see I'm flat here at x equals 0. I can see I have a flattening here at x equals 2. So what that means is these are flattenings. These little buggers are going to track down to x-intercepts for me on the other graph. I'm just graphing that guy. It's going to be straight below it. Bada bing, bada boom. And I'm going to track this guy down. It's flat. And I'm going to make that. Those are x-intercepts. My flattenings are x-intercepts. Now, after I find all my flattenings and I track those flattenings to my new graph, okay, I'm going to get rid of my dotted lines. What I'm going to do is I'm going to come back and I'm going to look for increasing and decreasing. So from here, I'll do here, if you like it this way, I have a flat here at 2, -2. I have at 0, I have a flat, and at +2, I have a flat. Okay? Between there, okay, so way out here, all the way, my function is always decreasing here, isn't it? Which means my graph of my derivative is always going to be negative. Now, between these two flattenings here, okay, what's happening? My graph is increasing, but I'm increasing from flat to flat. What that means is all of these values are positive on the derivative. Okay, they're all positive. Decreasing, these are all negative. Then from maximum down to minimum, I can see I'm decreasing again, meaning all y values are negative. And then from that flattening at 2, I'm increasing again, which means they are all positive. Now, what that means is, okay, there's only one way to kind of draw this, and this is going to be a possible sketch of f prime, okay? And then we're going to graph a sketch of f double prime off of f prime. But because this is always decreasing, these are always going to be negative numbers, I'm hoping we can come to the agreement that this is always going to be negative and never come back. But how the heck do I do always positive between two flats, okay, and then all of a sudden I'm going to go negative? Well, check it out. Right in the middle of these two flats is a what? A point of inflection. And what happens there, that's going to be when I am increasing the most. So what I'm going to do is I'm just going to place that little guy there. And what's happening is I'm increasing to that point. Okay, notice all these y values are positive, but I have steep ones up to that point. And from here, my tangent lines, they're getting closer and closer to the flat, meaning they turn to be less positive and they go back to 0. And then between my decreasing, check it out, point of inflection, because I have a change in concavity. Now, this one is decreasing, so watch what I went from a minimum to a maximum, and my graph had a maximum. Now I'm going from a maximum to a minimum. These are all negative. What happens is now I will have a minimum, and I'm going to stay negative, and they get most negative, and then they get less negative, and they come back to 0. And then from that 0, from that flattening, my graph is going to increase all positive tangent lines, and they never quit coming back. So I come right back up, and that's a possible sketch of f prime. Now what we're going to do is we're going to take f prime, and we're going to do a possible sketch of f double prime. All that means is my interpretation of this, okay, that graph is how I'm looking at this one right away. So I'm kind of thinking, oh, in my mind, I can think of it as f double prime. I'm like, okay, if I'm doing this all over again, this is my original f. And if, I'm just getting rid of that so I can draw that, my cute little number line underneath here, I really enjoy these number lines, because what I do with these number lines is I'll make, whoa, there's a flat. Where did that flat happen? And I can track that little dirty dog. That flat happened here at 1. I probably should have been a little nicer, and at -1 and 1. So what that means is when x is 1 on this one, I have a flat, okay? And over here, I have another flat at -1 and +1. I have another flat. When I'm looking to the left of this flat, I can see my function is increasing. Well, that means my derivative is always going to be positive. Between my flats here, I can see I'm decreasing, which means all those slopes are going to be negative. And then from this flat and beyond, I'm increasing, which means all my tangents are going to be positive there. So then what I do in order to graph my derivative, and ooh, check it out, flat to flat, what happened between these two flats that were maxes and mins? Ooh, what happened there? A POI, there's a point of inflection chilling out in the middle there. So what I'm going to do is I'm going to track my flats down here at -1. I'm going to put it there. I'm going to track my flat to +1, -1. I'm going to put it there. And because I'm increasing, okay, this function's increasing, they're always positive. From here, I got to be going up. This side, I'm increasing to the right of this flat. This side's got to always be going up. And what happened between here is I'm always negative, but the only way to show it's always negative is I got to get back and check it out. What happened there at 0? I had a most negative point. And then if I wanted to track that and draw the third derivative of this, I do the same thing over again. All I got to do, grab my line, and right here I'm like, oh, okay, at 0, I'm a flat. And to the left of that flat, I'm decreasing, which means I'm always negative. To the right of that flat, I'm always increasing, which means my tangents are positive. And if I had to graph my flat at 0, flats are x-intercepts. Decreasing, negative slopes, they're always negative slopes, to my flat. And then I increase from that flat, meaning always positive. And check out the connection here as I go through, okay? The original function looked like it was an x to the 4th power, isn't it? And then after I took its derivative, check out what happened. It looked like it turned into a cubic function. And then if I took the derivative of that one, whoa, Nelly, it turned into a quadratic function. And then if I took the derivative of that, whoa, Nelly, it turned into a linear function. And what do you think is going to happen if I take the derivative of a linear function? Well, if I looked at this and I went, I'm like, oh crap, I have no flats. There's no flats anywhere. This whole thing is increasing beyond everywhere. Well, increasing means positive tangents. How do I do that? The only way I can draw all positive tangents would be a horizontal line somewhere on any positive value of your choice, okay? From here, I got a pile of examples, and I'm going to walk through the first one, then I'm going to have you try them from there, and then I'm just going to write the answers on so we can shorten this video up a little bit, and I'll try to explain them as we go. But given here's f, we want to graph f prime below it, all right? And again, easiest way to do this, ladies and gentlemen, is, I've got a flat at 2. To the left of that flat, I'm decreasing, which means my slopes are negative. To the right of that flat, I'm increasing, meaning my slopes are positive. Well, how do I graph that? Well, if I have a flat at 2, 1, 2, I have an x-intercept at 2. And if I'm always negative and then always positive, means my graph can never have a bend in it. It always has to be negative, and it always has to be positive, meaning it's a line to the right and the left of those two, okay? And don't worry if your line kind of went like this, don't worry about it. The kicker is your flat in the right spot from above, and is your graph negative like it should be? Is it positive like it should be? That's the kicker of it, okay? And when I look at this one, Nelly, I'm like, no flats. I have no flats, but from negative infinity to infinity, and that's what my number line shows me every time, this sucker from left to right is decreasing, meaning slopes are always negative. Well, think about it. The slope of a line is constant, isn't it? If that's a constant negative value, how do I graph a constant negative value? Just like that. That's how I graph a constant negative value. And then we go to number 4. Okay, I have number 4. Number 4 is a tricky one, because what we got to do here is when I'm looking at number 4, Nelly. Green means go, baby. I'm seeing something wacky and wonky happening at 3. My question is that flat? Is that flat? And the answer to that is no, that is not flat. That is very sharp. That is very sharp from yesterday. And the reason I see it as sharp is if I had to draw a tangent line there, well, I could do that one, I could do that one, I could do that one, I could do that one. I mean, there's really an infinite number of tangent lines that I can draw at a sharp point, but there's only one that I can be tangent when it's flat. Okay? And because there's an infinite number of lines, I'm just going to back those up and I'm going to take those off. That is not flat. And what I should have been writing above my flats are little zeros for x-intercepts, but that's okay. What's going to happen here? This is not going to be 0. This is undefined. This is like an absolute value graph. Remember, the derivative did not exist at sharp points. So that just means does not exist there, but I'm continuous and I come together there. What do I notice on the left side of this? It is increasing always, which means it's positive. To the left of that sharp point, it's decreasing, meaning it's always negative. Okay, well, how do I deal with that? We deal with that very carefully. I just come straight to that same value of 3. And to the left of that 3, I'm always increasing,
That means it's never turning. It's always positive, which means it is a constant value to the left. And when I look at the right, okay, I'm undefined. That's why I put an open circle there. My derivative doesn't exist from there. And then what happened? Oh, when we did that, it was the opposite, going the other way, okay? Because this side's decreasing, they're always negative. But when I got right to that spot, it did not exist. And because it did not exist, that's why I used open circles, okay? I'm going to come to here. Ooh, here's a wonky one. Well, this is kind of weird because I'm missing something in the middle here. And what am I missing in here? Let me throw this little bugger in there. I don't really care if those are on there, but I do want red because what is going on in the middle of these two? What is there? Yes, there is a vertical asymptote going on there, okay? So what that means is, what does that mean? That means f of x never equals 0, okay? That means x can never equal 0 because it's a vertical asymptote. It's an undefined. So what do? I'm like, well, crap. I got an issue going on here. Something undefined is going on there. And to the left of this, my function is always increasing, isn't it? But is it always increasing constant like it was in number 4? No, it's always positive, but check it out. My slopes are really close to 0, and then they get steeper and steeper and steeper, and they get super steep. So there's a changing increasing here, just like there's a changing decreasing here, because they're super, super negative, and then they get closer and closer and closer and closer. Did you hear me say closer to 0? Okay, so when I graph this, I'm always positive, but as I'm going way out to negative infinity, it's getting snug as a bug in a rug. My slopes, my tangents are slowly approaching 0, and as I get closer to 0, they're getting super huge positively. That would mean boom, shakalaka. And when I look on the other side here for the other side is 0. Whoa, they are like super duper negative, close to 0. But as I go out to infinity, what are they getting? They're getting closer and closer to, you guessed it, 0. But because I'm super negative, close to 0, that gives me this. And that would be my graph of f prime of x off of that. And check it out. I can still throw this guy in the middle because my derivative still does not exist at 0. Woo! Kind of cool. A couple more yet. And then we're almost done. Now, number 6 is in your thing here, okay? But I specifically said, because sometimes it's hard to tell if they're flat or not, but I'm specifically telling you right now, that is a flat. That is a flat. So, like I said, a lot of times, when I come here, when I put 2, when I put a flat, what that means is that's 0 down here at 2. That's an x-intercept. Flat means 0 slope, because there's a horizontal tangent in there, but it's not a maximum or a minimum. So something different happens here, okay? So, and I can see I'm increasing, meaning always positive, to the left of the flat. To the right of the flat, whoa, it's still going up. It's still increasing, meaning it's still positive. What is happening here? Well, let's go back and let's interpret here. Left to right, super positive, less positive, less positive, less positive. And it gets less positive. It comes to, it gets through to 0. So what does that mean? Well, that means super positive, right? Super positive, super positive. The closer I get to 2, the closer to 0 I get. Well, what's happening on the other side? Well, as soon as I go past 2, they're still positive, but they're just a little bit. But the further away I get from 2, they get more and more positive. Ooh, remember what we called those in Algebra 2 Extended? We called those boink,
Bouncers. Yay, there's my f prime of x, okay? This graph interpretation is super important. If you're confused, make sure you ask. Here's number 7. Now the difference here is number 7 is not flat. That's why I wrote it in red, okay? So because it's not flat, okay, what's going on? Because I have changes going on here, there's something going on at 2, but what's really going on at 2? I don't know. What could that be? Well, if 2 is not really flat, but I still constantly, I'm increasing, all these tangents are increasing, well, what does that mean? Well, still, what is that? That's a point of inflection. The same way, that's a point of inflection there. The only difference is, here my point of inflection actually got to 0, or my slopes actually got to 0. Here, my slopes aren't going to get to 0. Watch out. Positive, 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 positive. Still most positive, but then there's still positive. But they never hit 0 in here, did they? They were still positive somewhere. I had something going on here, which means anywhere at 2, that just means, oh, that when I hit 2, that was like 2 comma some positive slope, meaning not 0. Over here it was 2 comma 0 slope, but over here it's some positive number, so that just rose my maximum up a little bit, which is a little wonky to think about. And then I do have one more. This one's not in your note sheet, so you can watch this one or you can add it. Again, is that flat? And nope, it's not flat. There's an infinite number of tangents that are going on there. So what does that mean? What that means is, here at 2, my derivative does not exist. It does not exist. And to the left of that derivative, I'm always increasing, positive, but notice these are changing. There's nothing constant about the left side. They're approaching something. It looks like they're getting closer to 0 here because it's starting to flatten, okay? So we can interpret that as flattening, but right there at the point, it's not flat. So I'm going to come down here to 2, and these are increasing, meaning positive tangents, meaning, come on, Kruger, I got to write a new 2 in there, and moving this up a little bit, and I'm going to come back here, I'm going to put my 2 here, and because it's not flat, but because it's sharp, it doesn't exist. If it doesn't exist, it's open, okay? So I'm very, very way out here at negative infinity. I'm very positive, and I come into 0. What does that look like? That kind of looks something like this. And don't think that that's a vertical asymptote, because it's not. It's parabolic. It appears to be parabolic. And then from this side, I'm decreasing, meaning always negative. However, that's a line where the slope is the same everywhere. The slope of a line doesn't change, and these are always negative slopes. Now check it out. Over here, my slopes change. They're all positive, but they're changing because it's a curve. This is a line, so slope doesn't change, but it's always negative. How negative? They didn't give me it, but it's going to be constant negative, okay? Last one, I'm telling you where they're flat. What I'd like you to do is give this a shot, try it on your own, and I'm going to draw it and compare it. Okay, so these are all flats, okay? So what I'm going to do is I'm going to draw this little rascal out. Remember, this is infinity down here, this is negative infinity here. I have a flat at -1, and a flat interprets to a 0. So flat means 0, okay? And the other thing that's really important that I haven't done is know that this is my f prime line to see that this flat is a 0, I'll be consistent with what I did. So I'm going to call that a flat, and flats are zeros. So I got one there. I got one at 4 is going to be a flat, which is another 0. And I got one at 8, okay? And I got one at 8, which is a flat, which is 0. We can see that. We can see those tangents there, okay? And -1 could be in question. We don't really know, but I'm telling you it's flat. That's why it's going to be a 0. Now, what I see to the left, up to my first flat, I'm increasing. I'm increasing, meaning positive. I'm changing, increasing, okay? To the right of that first flat, I'm still increasing, positive. You know what the increasing, flat, increasing, that means bouncer. That's exactly what that means, okay? So that's really what I'm picturing here. And then I increase, and then I go here, 4 to the right of that flat, I'm decreasing. And then to the right of this flat, I'm increasing again. So really, what I tried to do here with this is increasing to a flat increase. That's really showing that. It's really showing a flat in there. And then I'm increasing on the left side, and then I decrease here. So that's kind of really showing this at that flat. And I should keep that, but I actually touch 0. Then I decrease and I increase, so that should be this, right? So when I do that, when I take that across to my bottom, okay, my flat tracks down, my flat tracks down, my flat tracks down. Increasing, increasing is bounce right there. It bounces. And then between this flat and this flat, well, I'm increasing the whole time. And right in the middle of there, right around 2, okay, I can see, ooh, what is that? Ooh, point of inflection. So I'm increasing, and then I'm still increasing, but not quite as much. And I come back to my flat. And then on the other side, I decrease, and then I increase. Well, that should show me this somewhere between there. And right in between there, right here, when I'm showing this, I got a point of inflection somewhere in at 6. And then I go off forever. So Monday, we are going to be sketching graphs from F prime back to F. So think about these hard, look at them, and do what you can do well.